The problem, we're going to try to do this as quickly as possible so you're out of here by maybe 15 after, okay? It's a bit longer session today because there is so much to cover. The problem that I did last time in the review session and went over it quickly is you have an object that is skidding initially, like a bowling ball, skids and then rolls, okay? So that guy is too heavy. I need another bottle, something that will demonstrate. Oh my God, do I need your? Am I? One of the more comprehensive problems in mechanics is, it combines everything really. So you have a ball that is sliding initially, slides for a bit, and then, so sliding, and then it begins to turn, and eventually it rolls, okay? So last time what we said was the only force acting on this object is the force of kinetic friction. And that force is known. It is mg mu k, okay? Kinetic friction is n mu k. The normal is equal to mg. So we know the force of friction acting on this. The only force acting on it is the force of friction. It's kinetic friction, and that is pushing it back. So as the object skids, it is slowed down, and by the force of friction. So the velocity will drop, but also because the force of friction acts this way, it's going to speed up the rotation till we have omega pick up. V will come down, omega will come up till they meet. So the way we did it last time in detail was as follows. We said V is going to drop as V naught minus AT, and then omega is going to pick up as, because it was 0 plus alpha t, and then eventually, this is a function of time, one will pick up, one will go down until V of t equals omega of t times r, okay? And we had three equations, three unknowns. These were V final, omega final, and t. So you had to solve three equations, three unknowns to get this problem done. What we also said was, what is A? A is equal to what? F kinetic divided by m, and that's mg mu k divided by m, that's g mu k. Okay, what is alpha then? We have A check. Alpha, because the force of friction acts this way, that's going to slow the object down, but also alpha is given by, torque about Cm is I Cm alpha, and alpha was tau Cm divided by ICM, and tau was the force times R divided, and the force of kinetic friction times R divided by 2/5 mr squared. And that gave us, because the force of friction is mg mu k, 5/2 g, 5/2 what? 5/2, g mu k over r. So check you have that, check you have this, you plug them in there, and this reduces to a three equation, three unknown problem. That's a long way of doing things, okay? That's the long way of doing things. We can do this using what, guys? As we did last time, but I rushed through it. We can do this using angular momentum. And angular momentum, guys, you have to remember that the angular momentum of an object, okay? So look at this. I have this object orbiting me because I am so magnificent and amazing, okay, guys? So Alex doesn't agree, right? I saw that smirk. Okay, so this guy is orbiting me. This guy has angular momentum about me right now, right? So, okay, so what is the angular momentum of this object about me? It's moving this way. It's r cross p, right? But then on top of that, the object does this. So the total angular momentum is what? On its own, if the object was just spinning, it has angular momentum I omega. But if it's orbiting me too, orbiting whatever, it's got r cross p. So the total angular momentum of an object moving in general is given by any object that happens to be, let's say, you have a center here, and you have an object that is orbiting the center. It has VCM right now, and it has omega this way. Okay, as it goes around the orbit this way, we say what this is R. Right? Then okay, I made it perpendicular. It doesn't have to be perpendicular. Right? We say that the total angular momentum L total is equal to L orbital plus L spin. Okay, and well, and these have directions, right? Because L, depending, they could be, you know, if the object is moving this way and spinning that way, you add them. But if spinning that way, you subtract, right? So L orbital is R cross PCM. Okay, keep that in mind. Plus ICM omega. We're accounting for both angular momenta. That is the total angular momentum of an object about any point P. Okay, for any point P, so point P could be here, then you had R cross P, so this is about P, L total. All right, we're going to use that concept now to solve this problem in one line. And as a matter of fact, these three problems that used to show up on finals a lot, take a lot of time to solve. If you use the spin orbital approach, you're done in 1 minute. You will need that time because other problems are going to be taking a lot of time from you. Right? Okay. So guys, can you please now, based upon what I said, can you use the concepts of orbital and spin angular momenta to solve all three problems? Here, you have an object that was sliding, skidding, and in a roll. Okay? The second problem is the object you're playing around with a bowling ball, so you decide to give it a backspin like this, and that's what happens, right? So really interesting question would be, how does this actually stop? So what you could have is this object come back at you, kind of like that, okay? Or go forward, okay? Or just stop. All right. Bow to me. I think I said that last time too. It's getting stale. Okay. So the last problem that I would like to tackle, and I will at least give you tips to finish these at home if you get antsy when you go. The last problem looks like this. The last problem is like this. Right? Like that. All right. So if I hit you, Jasmine, I'm not responsible for your safety. Ow, that hurt. All right. No, that's it. Oh, for Pete's sake. You're appealing to my ego, you. Oh! I am not destroying university property. It is fixed. All right. So, thank you. The last one is you deliver a blow, and there are two versions of this problem, okay? You deliver a blow, okay, yeah, so this is about whatever, so many minutes ago was the start of the second video, okay? When I started drawing stuff on the board for rolling motion, right? If they can get that done, that'd be great. You deliver a blow to this, guys, and you could deliver the blow here at the center. You could deliver the blow here or there, okay? Depending on how you do this, whether you consider friction first or not, you can ignore friction and say you kick it here, it's got top spin. What you saw in front of you was conservation of two things. Conservation of linear momentum plus conservation of angular momentum, okay? Or not conservation. Change in linear momentum and change in angular momentum. And I could show you, I'm going to show you how to do this here. The problem can be done by saying initially there is no friction. So you hit this here and it skids, and it could, you know, if you hit it low, it can have backspin. If you hit it high, it can have top spin. Or it can be done with assuming there is enough friction to prevent it from rolling, right? Where you hit it here, but there is no skidding, and what's going to happen after, right? We'll see. I will do one possibility for you, and then the other one you can think about for your for later. Right? So what I'd like to do now is give you guys about 2 minutes to set this up with. We know how to do this using forces. I want to set it up with angular momentum. Okay, guys. So to see how easy this is with angular momentum, right? We're going to say that, well, to use angular momentum, we need to conserve angular momentum. So I'm going to begin from the end, saying L system final is equal to L system, or L system initial, equal to L system final. Okay? But how does that work? I mean, L, what? Obviously, momentum is not conserved. Linear momentum is not conserved. Why? Because, I mean, when is linear momentum conserved? Remember that F is equal to dP by dt. So if the force acting on the system is not zero, then dP is equal to F dt. The force times the time gives you the change in momentum. Now, if F external is zero, then dP by dt is zero. F net or external or whatever you call it. Right? So the rate of change in momentum is the total force or net force, external force acting on the object or the system. Right? So on the system here, we have the ball acted upon by. So when does momentum change? When you hit something with a force, you change momentum. If you don't hit it with a force and it's moving in outer space or on ice, the momentum does not change. Right? So linear momentum will change if you have a force acting on the object. Okay? Now here, we have a force acting on the object. That's the force of friction. This is kinetic friction to start with. So momentum is not conserved. P is not conserved. Right? So P here is not equal to P there. But what we're trying to say is that maybe we can conserve angular momentum. Now, the advantage we have is in remembering or trying to remember that angular momentum is taken about a point. Linear momentum is just linear momentum. If you have a force acting on the object, it will change the linear momentum. Right? But angular momentum, if you take it about this point here, and that's just some arbitrary point on the road, on the surface, call it point P, then what can we say? dl, so this is point P, dl, okay, by dt, by the same token, by the way, guys, we didn't talk about this, but what is L equal to? L is I omega. What is dl by dt? I what? Alpha. And what is I alpha to equal to? F equals ma, F net, and tau net is equal to what? I alpha. So that's tau net. Okay? Now, what is missing in this discussion is the fact that angular momentum and torque and moment of inertia need a point of reference. Right? So you don't say the object has, this object has linear momentum, and it's linear momentum. Right? It has angular momentum as well, and that angular momentum depends on what are you taking the angular momentum about. This object moving in a line has angular momentum about you, about him, about. So the angular momentum changes based upon the point of reference. Right? So now we're taking this to be the point of reference, and we're saying that dl by dt is equal to tau external. But about what? Well, about point P. All right? So how does that work? Well, dl by dt is equal to, what is tau external about point P? What is the only force acting about point P? F kinetic. And what is tau? That's the tau of F kinetic about P. 0. That is 0. Why? Because F kinetic points into the pivot. Okay? This is not going to create any torques. We have something to play with in that we can say now that L initial about P is equal to L final about P of the system. All right? And to get the L initial and L final, we're going to use our spin and orbital angular momenta. Okay? So this is case 1, or situation 1, and this is situation 2. And how does this work? Well, the angular momentum initially, or finally, we are going to use, what is it? This stuff here. Right? We're going to use our expression for total angular momentum. So let me make some room, because we're not going to use this stuff. So L initial and L final are both what? L momentum total is L orbital plus L spin initial equal to L orbital plus L spin final, right? So, and that's about point P. Okay? Initially, we only have orbital. Spin is 0. That goes away. So L spin is what? From there, it's R cross P. So this is R, and this is P, this is MV. P equal to MV. So initial angular momentum is what? R cross, that's R cross P initial, and that becomes R, P, R, MV sine theta. But pay attention here that R, P sine theta, okay? Focus on, again, spotting perpendiculars, R sine theta, okay? We have, this is theta, that is theta. R sine theta becomes simply what? R. So that becomes R times MV CM, okay? That's the ball moving, becomes equal to, finally, when the guy's over there, right? This becomes R, one more time. This is R, and now this is P final. So this is P final, okay? We call this V. So let's call this V going in, MV, and this guy now has V prime, okay? So that is R cross P initial, MV initial V, is equal to, over here, in the final state, we have two things happening. We have R cross P plus the I. So from here, guys, the total angular momentum is, remember, an object moving around this way, R cross P plus I omega. So that's equal to R cross P. Again, R cross P is R, P, this is R, this is P, this is theta, this is theta. R, P sine theta becomes simply, again, RMV, RMV prime plus ICM omega prime. And this problem is done in one line, really, right? Oh, no. I apologize, guys. Thank you, Stefan. I wasn't looking. I crossed out the wrong one. Spin is 0. Sorry. Orbital is R cross P, and that's, okay, one more time. That was just a typo, okay? Bad typo. So, The orbital is R cross P, and that's R and V. All right, that's okay. The spin, there is no spin. Okay? So remember, if you have an object going around, R cross P gives you orbital, and then you have spin. In this case, the spin is 0, orbital is not. So how do you finally do this solution then? You say, well, guys, pretty easy, right? Because now, over here, R mv initial equals to R mv prime plus, what is ICM for a sphere? 2/5 mr squared omega prime, right? And now R omega is V, so this becomes R mv equal to R mv prime plus 2/5 m r v prime. Okay, all right. So the r's cancel. Okay, guys, the r's cancel, and the m's cancel, and you get that v prime is equal to, what is that? You gonna give me 5, 10? How does that work? 5, 7. 5/7 of v. Okay? So you didn't even need you did not need anything. Not R, not M, not friction, nothing. On your own, using what you saw there, use the spin orbital approach, right, to find the final speed of this guy. Okay? Use this point P here. But you are using a different principle. Not spin orbital anymore. It works out. All right, folks. So, without much ado here, borrowing what we learned from there and putting it here, we say what, guys? This had, now about point P, you have to pay attention here. About point P, which way, so L initial, L system initial is equal to L system, or object, not system, final, right? So why? That's about point P. Okay, because the only force acting is the force of friction, F kinetic, and its torque is 0 about point P. So we can say that, but clearly identify that this is point P. What is L initial about P? It is equal to L orbital plus L spin at initial equal to L orbital plus L spin final. I'm being a bit careless with signs, with vector signs. These are vectors, all right? How do you determine signs for these things? You say maybe this is positive if you want, and let's work with this a little bit. If that's positive, guys, then what? Obviously, if that's positive, spinning this way is positive, right? That's spinning the opposite way. That guy is definitely negative. So it's equal to negative ICM omega, right? Now, what about the orbital part? Which way is it turning about? How do you do that? It's just like torques, right? So you stretch that, you find the moment arm, and that's going this way, right? Or you could use your right-hand rule, or just do this, right? That guy is going this way, kind of, right? So L orbital then is R mv, right? And that's equal to what? R mv prime plus ICM omega prime, okay? What do you know here? You're given this V, you're given omega, and finally, what's unknown is these guys, but you know that V equals omega R, so you write R mv prime plus 2/5 mr squared omega prime equal to R mv prime plus 2/5 R mv prime, and that's equal to 7/5 R mv prime, okay? Yeah. You're given V and you're given omega in a problem like this, yes. Right? So, guys, so you have that now, and all you have to do is this is given, that is given, and you can find out what. Now, V and omega are not related necessarily to start with. They're not related. So, okay. So the last thing I want to do, guys, we're a little bit over time, but the last thing I want to do is, and as I said, maybe I'll pause for 2 minutes. Let you digest both problems. 3 minutes. Again, about this point, what I'm going to do is say, well, the point is here. Okay, whatever. Why? Because now this is so powerful, you can solve any kind of problem with it like this. Right? You say the following. There has to be friction, though. Now, this has two possibilities. One is you kick it and it just rolls. That's possible. It can also do what? It could also skid a little bit and then roll. If you want to use the forces approach, it's very difficult. Okay? Because you have to account for friction, and when you're doing change in momentum, delta P or dP by dt, dP by dt is equal to F external, and that force of friction is a variable. It begins at 0, grows up nonlinearly, and then becomes kinetic. You're going to go from 0 to maximum static friction to it's not something you want to deal with. It's a bit of a muck, right? So conservation of or using angular momentum is way more powerful, because you say what? That is not something you want to use because this force of friction is a bit of a mess. So you say this is point P, and you say, well, dL by dt is equal to tau external. All right? And that's all about P. So observe this, guys. So this says now that delta P or delta L, dL is equal to tau external times dt. And these are vectors. Right? So we're not really, respecting the vectors right now too much. Doesn't matter in this problem. So delta L then is equal to tau average delta T. All right? About point P. Okay? So the question is now, what exerts torques about point P? Does this? Friction is going to act this way probably. I don't know. Maybe it'll act that way too. As a matter of fact, you don't know. Depending on where you kick it, force of friction could be acting this way or that way. I'm not sure about this yet. But there is a force of friction here. But the only thing that exerts the torque is what? So now, then what is the torque of F about P? R, okay, sorry. I'll do it in red. That is equal to R cross F. Okay, R is this way, that's F, or just keep it this way, it's fine. So it's R cross F, R to here, and then cross F. Okay? Now, you have R cross F, and that's equal to what? Torque is the torque of the force now that you apply is equal to, delta L about P is the torque of the force about P average times delta T. We're taking this to be the average. All right? So the change in momentum, okay? The change in momentum is equal to that. What is tau about, what's R cross F? So it's RF sine theta. That becomes just RF. RF delta T. That is your delta L. 3R over 2, yes, correct. If I was hitting it here, in the middle, it'd be. So that distance is 3r over 2. Not r. Okay? So what is that equal to? That's equal to the change in momentum. That's equal to, so that delta LP about P is equal to 3/2 F R delta T, and all that is given. That's equal to L final minus L initial. And L initial was what? 0. So that's just L final. And what is L final equal to? When this guy is moving this way, we have V and we have omega, right? So we say that 3/2 F R delta T, and they're all given. And this should be really what, guys? You say F average if you want, or F is constant or whatever, right? So the force should not change, or that's the average value of the force. That's equal to L final is equal to R cross P, that's orbital, Cm, plus I Cm omega, right? And then 3/2 F R delta T is R mv, because it's RP sine theta, and that's theta. R sine theta becomes just R. Right? And plus ICM 2/5 M R squared omega. And now you can, using that V equals omega R, or omega equals V over R, you can find V using omega equals to V over R. Okay? Can you see? So solve for V using omega equals to VCM over R. That's Cm. Alex, you happy? Partially happy. All right, guys. Thank you so much, you troopers. Good luck on your exams.